So I do want to give you some information on gas phase versus solid and liquid phase because there is a difference between these two. Now typically, practically, when we look at FTIR of solids, we're only looking at roughly 2 wave numbers of resolution. So 2 inverse centimeters is about the best we can do, and there's a practical reason for this. Whereas with gas, we can go as low as 0.1 wave numbers. So first of all, why would we even care about taking 0.1 wave numbers when we can do 2 wave numbers just fine for solids and liquids for identification? The second is what's giving rise to this. So there's something that a gas can do that a liquid and solid can't do, and this is rotate its molecules. Now, again, I'm kind of oversimplifying the physics here. There is a little bit of rotation in solution, but not nearly as much. So if we were to measure an infrared spectrum of a solid, we would end up getting a broad distribution. So things that sort of look like this. Whereas with a gas, we'll start simply here, we should basically see one spike corresponding to the vibrational mode of that individual molecule. Now, there's width to all these peaks associated with Heisenberg uncertainty. So we don't measure a single frequency of absorbance because we would know the precise energy of the electron if we did that. So there's a Lorentzian shape already in there. But when it comes to liquids and solids, they are near other molecules. They have physical proximity to each other. Because of this, they tend to broaden each other's peaks out. Especially with alcohols, what we end up seeing is that these OH groups like to exchange electrons. Because they're associating with each other, we get a broader distribution. So we have a Lorentzian distribution plus the distribution of the atoms around each other. This is not true for a gas. For a gas, they're going to act ideally. They're going to act like they don't see each other, and so we're able to get much better resolution. Now, particularly with solids, there is an additional effect that typically solids have a crystal lattice. That crystal lattice vibrates in response to the infrared spectrum. So it's not that you're just vibrating these bonds. These bonds are vibrating inside a rigid lattice, which begins to vibrate the lattice itself. So when I used to take measurements on solids, the reason why we can never drop beneath 2 centimeters is that we would start getting these weird chops in the spectrum. And what we were seeing was that you're vibrating the molecule, well, it begins to vibrate the solid as well. And eventually that vibration gets picked up by the IR. So you would see spikes that had nothing to do with functional groups. It had to do with lattice vibrations. Again, gas phase molecules, there's not a huge crystal lattice deal, so we don't see this. Now, there is an additional complication with gases. Because they are free-floating molecules, they can also rotate. And that rotation has a frequency associated with it as well. So whereas with solids and liquids we get these nice broad peaks, not only with a gas do we get a nice defined Lorentzian shape, we're also going to get little spikes off to the side. So you may say to yourself, well, why would there be multiple ones? Well, actually, this is kind of the cool thing. It can rotate, right? And the vibrations here are associated with electronic energy levels. These little spikes here are associated with rotational. So these are what are called roto-vibrational bands. So if you ever see a gas phase molecule, you're not going to get just one sharp peak. You're going to get a sharp peak with a whole bunch of little peaks beside it. And these peaks correspond to the rotational energies associated with that molecule. So something like HCl, yeah, the HCl molecule vibrates. That's going to be your big peak. But we can also have it rotating at different rates, and those different rotation rates are picked up here inside the spectrum. So this is the big difference between gas and solid. Gas, we can get down to 0.1 wave numbers because we can start seeing roto-vibrational bands. We start getting really well-defined peaks. With the solids and liquids, we're typically going to stick to 2 wave numbers. The big reason is that all this broadening we get is due to the fact that these atoms and molecules are associating with each other. So we lose a lot of resolution. We also start getting artifacts of lattice vibrations if we have a solid. So if we try to get beneath 2 wave numbers, we're going to start picking up on just the practical aspects of this measurement.